Hello everyone, welcome to my class. Today I am going to cover vector fields. First, quick overview. In Calculus 1, we studied functions from real line to real line, which we call single variable functions. For example, f of x equals to y. So here input is real numbers and output is also real numbers. And in Calculus 3, so far we studied functions from R to multidimensional space Rn, which we call a vector valued functions. So for n equals to 2, for example, we denoted vector valued functions by Rt equals to xt, yt. These are the components of vectors function. And in another function, we studied functions going from multidimensional space to real line, which we call a several variable functions. For example, for n equals to 2, this is we denoted by z equals to function of x and y. And now we will study functions. I'm just showing the pattern of the functions here. Now we are studying the functions going from multidimensional space to the same multidimensional space, which we call a vector field, and we denote it by vector functions capital F. So for us, we pick n equals to either 2 or 3. So let me define our vector fields next. So the vector fields are functions going from Rn to Rn that assign vector to each point in the space. So for example, in R2, it takes an order pair and gives us a vector starting from that point. So xy is now a vector. In this space R3, it takes an order triple xyz and gives us a vector x component, y component, z component starting from the point. Just a visualization. So this side is our domain is I'm giving example in R2. So these are all the order pairs, and then the vector field takes a point and gives us a vector starting from that point. So these all are the vectors now for each of these points. I mean there are many points and we have many vectors here. So just take a point and gives a vector starting from that point. Starting from that point, the vector, the vectors, the vectors, the vectors. So here I think there are a bunch of vectors here. So, and obviously small comment here, of course, it is impossible to do this drawing the vector for all points, but we can gain a reasonable impression of f by drawing it for a few representative points in domain. So now quick note, vector field starts at the point. So take a point and construct a vector starting from the point. Important concept, important note. 2, pictures of vector fields look like a needle diagram then. See a bunch of needle diagrams pointing in different directions. Note number 3, since vector field is a vector, we can write it in terms of its component functions. Say pxy and qxy as f equals to pq or pxy comma qxy by using unit vectors pi plus qj. And if it's in the space, then we do have f of xyz equals to pqr. The quick example, the gradient of scalar functions, grad f, is a vector field, and which is called a gradient vector field. Let me scroll down. Let's do a quick sketching of the vector field. That's better. So sketch the vector field given by f equals to 5i. So it's a constant vector field here. So at every point xy, we draw a vector with component 5, 0 parallel to x-axis. So for pick any point, and then the output is just a 5, 0. Pick a point, you go the 5 unit toward the x-axis, positive x-axis. So each point is 5, 0. This will go to the 5 unit parallel to the x-axis. So that's a visualization of this vector field. Now let's go example 2. Let me scroll down. That's better. So sketch the vector field capital F equals to the component with negative y and comma x. First, let's make a table. So pick a point, the xy is a point, and fxy is a vector field. So at 0, 0, we have the vector 0, 0. At 1, 0, so we put here 1, 0 becomes negative 0, 1, but which is same as 0, 1. And let's pick negative 2, 2. If our input is negative 2, 2, negative 2 and positive 2, then our output is negative yx, so that means you bring this to this side, which is negative 2, by that sign, and you flip x this side. So we are just switching x and y and putting minus sign for the first one here. So we have this one. Then let's sketch this graph here. So for example, let me make this bigger here so that you can see here. So yep. So let's pick a point. Start from the 1, 0 point. Here is a 1, 0. Then the output is 0, 1. So then 1, 0. So this is the output 0, 1 vector. Let's say pick another point. Let's say minus 2, 2. What is minus 2, 2? So minus 2, 2 here. The minus 1, minus 2, and then 1, 2. So minus 2, 2. What's the output here? Output is minus 2, minus 2. So then minus 2. First go minus 2. That means opposite in the x-axis. So that means negative x-axis direction. So here is a 1, here is a 2. And then go negative 2 down. So negative 1, negative 2. So this is the vector output at this point, negative 2, 2. Let's say add 3, 0. So 3, 0. Output is 0, 3. So 3, 0, I'm here. So then you are going 0. So that means no x component, only y component is 3. Then go component 3. 1, 2, 3. So that's the idea now. So then here it seems a circular motions here. It's just going around the circle, and if you are far from the origins, your vectors are longer and longer. So good. So let me zoom out. So now we can see a pattern that with all vectors are tangent to circles, centered at origin, and vectors farther from the origins are longer. So this is a vector field for this given vector field. So we sketch here. And think for a second, there are a bunch of vectors here, by the way. Okay, so now let's move on. So the quick aside here, so on these vectors, if you rotate this vector field and divide by its magnitude, then all of your vectors have unit directions. All of the vectors are unit vectors. Yeah, unit vectors, which I sketched the graph here, and all of these are clockwise. Now let's move on. Let's do example 3. Find the gradient vector field of scalar functions. Little f of xy equals to y times sine xy. So we just take the partial derivatives here. So gradient f equals to fx fy. When you take a partial derivative of f with respect to x, take y constant. When you take a partial derivative of f with respect to y, take x constant, which is here. Similarly in the b, f of xy z equals to x squared plus y squared z squared. Now that's a function of 3 variables, scalar functions. And the gradient of f equals to simply fx, fy, fz, which is 2x, 2y, 2z. So great. So we finished these sections. So now just a heads up, and now we try to put the calculus on the vector field. Okay, so our vector field is f equals to p comma q. Then we define a continuity of a vector field component wise, and in the next section we'll talk about the integral of vector fields, and we call the line integrals. So great. So we finished these sections. So thank you.